Welcome back to the course in statistical mechanics of phases and phase transitions. I hope you are having a good day, and I hope also that after listening to this lecture, your day will be somewhat better. So let's begin by recalling what we did in the previous lecture. So we discussed about models and what crucial role they play in statistical physics, and we built on some ideas for making models. So the three main points were to identify an arena, to identify the degrees of freedom that would sit on these arena points, and then formulate a Hamiltonian or an energy function that depends on the configuration of the degrees of freedom. And we pointed out that symmetry plays a very important role in building this whole model. And we looked at two models, the Ising model, and we also briefly looked at the interacting particles model, which is a model in the continuum. And we also ran into some unresolved issues. So the question was, when we talked about the Ising model, we simply imposed a Z2 symmetry. So the key question is, how do we actually identify symmetries, or what kind of symmetries do we adopt in a given problem? And then we wrote down a certain Hamiltonian. Then you can always ask the question, is the Hamiltonian unique? Can we write different Hamiltonians? So these are some of the questions that came up. And in this lecture, what we will do is, we will take a deeper look at symmetries. We will show that, or we'll point out that there are two types of symmetries. One are called arena symmetries, and the other is called internal symmetries. And then we'll move on to understanding energy scales in the Hamiltonian. And we'll again find that there are intrinsic energy scales and extrinsic energy scales. And then based on this whole discussion, we will realize that there are certain dimensionless coupling constants that you can define in any problem, and the physics will be governed by those dimensional coupling constants. So those will be the natural parameters to view the phase diagram. Okay, let's start with the discussion of symmetries. So obviously, all of us know this. Symmetry is a very important concept in all of physics. We have been taught this at very early undergraduate courses. So naturally, what is really a symmetry? So what we do is we observe some phenomena in a certain frame or a setting, and by a frame here I don't necessarily mean a coordinate system, and it will become clear as we go along. And then we change the frame and observe the same phenomena in the system, keeping all other conditions identical. If the same experimental outcome is obtained in both the frames, then the change of frame describes the symmetry of the system. So this is a very conceptual way of describing this. While this may be very appealing from some physical perspective, it's important to also put some mathematical flesh onto this. So the question now is, how do we describe the change of frame? So usually this is called as a symmetry operation, and what the symmetry operation does is it transforms your degrees of freedom in some way. Now a symmetry operation is called a symmetry if it also leaves the Hamiltonian of the system invariant. That is what is being pointed out here. If the Hamiltonian is also left invariant by a symmetry operation, then we would call that symmetry operation a symmetry. So this is the upshot of this slide. A symmetry operation is a symmetry if it transforms the degrees of freedom in a certain way and keeps the Hamiltonian unchanged. So let's look at some examples from our early experience. Recall that when you were in high school, you were asked to compute the acceleration due to gravity by measuring the time period of a simple pendulum. Now, you know, your class may have had 50 students, and they were divided into batches of 5 or 10, and they were given tables to do experiments on, and the tables were not all in the same place. They were in different places in the laboratory. And everybody did their experiment, and to a good approximation, everybody found the answer of G to be 9.8 within error bars. And what this means is that it didn't matter where you are doing the experiment, you got the same value of G. So it indicates that there is some idea that where you are doing the experiment doesn't matter, and that is a way of saying that the system seems to have a translational symmetry, at least for translations on the scale of the size of the classroom, let's say 10 meters by 10 meters. So what I'm trying to point out is that the simple pendulum experiment suggests that there is an approximate translational symmetry on the surface of the earth if you stay within some small distances. Same thing, when you went to the chemistry lab, you took an acid and a base and added them together and you got salt and water, and you would get the same thing irrespective of which part of the chemistry lab you did the experiment in. So that process also seems to have translational symmetry. It seems to indicate that there is translational symmetry in the physics underlying all of this phenomena. Directly related to our previous discussions, the phase diagram obtained by different groups in the same department, for example, will be the same if you take CO2 and do experiments very carefully and in a very controlled manner. So this again suggests that the physics there has some translational symmetry. Okay, so this was examples from what laboratory experiments we have done. So we'll move on to a magnetic example. There are many insulating magnets where the spins prefer to orient along certain crystallographic axes. This arises from a physics called a single ion anisotropy. I will not discuss what the origin of that physics is, it's just there. What that means is, an example of a material that has this is lithium holmium fluoride, and it's a tetragonal crystal, and the spins prefer to align along the C axis, this axis. If you measure magnetization in this material as a function of temperature, so I'm measuring the magnetization as a function of temperature, you will see the following. Up to, as you cool down from starting from a high temperature up to a temperature called Tc, the critical temperature, there will be no magnetization in the material. You will find that the magnetization is 0. Then what happens is magnetization spontaneously appears below Tc. What do we mean by spontaneous? It's important to understand this. Spontaneous means I have not applied any external magnetic field. In fact, I am doing the experiment in an isolated cage where I have tried to isolate all stray magnetic fields, and yet the system by itself produces a magnetization. Now what we observe is that the magnetization always points along the C axis, and this is how we conclude that the spins prefer to be wanting to be aligned along the C axis. And second point is, if you repeat this experiment, so for example, if you take it back to high temperature and bring it back down, then it's not that the magnetization will always appear along the plus C axis. You could also have the magnetization appearing along the negative C axis. So 50% of the time you will get magnetization doing this, which is that it starts to increase at Tc and goes to a positive value and saturates to 1 in some units. And 50% of the time you will see that the magnetization is coming down negative and it will go saturate down to negative 1 as T is reduced to very low temperatures. So this is what we see. So what can we infer from here? So the lessons we learn from this is that magnetization is always along C axis, indicates that spins in the ions are pointing either along the plus C axis or minus C axis. This suggests that the system has some kind of Ising degree of freedom, means you can think of the spin as if it is either pointing up or pointing down, which means we can give it the possible values of +1 when it is pointing up and -1 when it is pointing down at each lattice site I. The spontaneous magnetization is randomly along plus C and minus C axis, which means that the energy of, let's say, the all up pointing configuration is same as the energy of the spins pointing all down. Okay, this strongly suggests that there is some kind of global spin flip symmetry described by the Z2 group, as we have seen in the last lecture, at play in this model. So if you state this mathematically, the spin configuration curly C here, which is the set of all spin values at each individual lattice sites, carries a representation of Z2. What do we mean by that? I can mathematically perform a spin flip transformation, which is indicated by this F, and the flipped configuration is a configuration C prime, which will flip the spins at each individual lattice site, means Si goes to minus Si. And what the experiments also suggest is that the energy of these two configurations are equal, because they are showing up 50% of times they are up and 50% of times they are showing up with the negative value. And this is what the experiment shows. So this example clearly shows that the arena, degrees of freedom and the Hamiltonian, the Z2 symmetry of the Ising model are all inferred from experiments. Now, this is how a lot of advances in physics were made. For example, physics has very beautiful examples of people guessing the symmetry. A very nice example is the U1 symmetry in superconductivity, that's Ginzburg and Landau, and the SU3 symmetry in particle physics by Gell-Mann and so on. All of these were motivated by looking at experiments. Now, this is how things were happening. People looked at experiments, they guessed symmetries, but we have also moved on, and in fact, nowadays what people do is they think up of a symmetry and they study a problem with that symmetry and see if it produces some exotic physics. And I am showing you here a reference to a paper in which they have studied non-abelian anyons in a system which has a certain type of D4 symmetry. D4 is some kind of dihedral group. So I invite you to take a look at it in your free time. Okay, a little bit more on symmetries. We have seen now that there are two types of symmetries if you think about it. The first type of symmetries are arena symmetries. Remember what we found when we did the simple pendulum experiment at different places in the lab. We said that there is translational symmetry. That is like you are doing something to the arena, or you are thinking of something happening on the arena. Then there are another class of symmetries called as internal symmetries. These are like the spin flip symmetries I talked about. I don't do anything to the arena. I just transform the degrees of freedom in the same place. Okay, these are internal symmetries. Now, arena symmetries, as I pointed out, are associated with transformations relating to the arena. These are example translations, rotations, reflections, and internal symmetries as associated with the transformations in the spin space. So, for example, the Z2 global spin flip symmetry that we talked about are examples. Okay, so let's start by discussing arena symmetries. And we will first discuss continuum arena symmetries. So, these are symmetries associated with changing the arena viewpoint, right? And these include translations, rotations, reflections, inversion, and compositions thereof. You could translate and then rotate and so on. You can do a variety of things. Now, the important point to note is that the continuum arena symmetries are always continuous. What do we mean by that? Say, for example, if you have rotations. Now, you can rotate by any angle that you wish. You can rotate by 30 degrees, you can rotate by 31 degrees, you can rotate by 30.1 degrees, you can rotate by any angle you wish. So, in the sense that the parameter that enters the symmetry operation, namely say the angle of rotation, is a continuous parameter, and this is why we call them continuous symmetries. So, the important thing about arena symmetries is, even if you didn't have anything else, the symmetries can act on the arena itself, right? So, for example, if X is a point in the arena and then an arena symmetry of operation G maps it to a new point X prime, which is, we'll just functionally denote it as G of X. It acts on G acts on X, sorry, and takes it to a new point X prime. And I can draw a picture for this. So, this was the original point X. So, G acted on X and it went to a new point X prime G of X. Okay. But remember, I also have the degrees of freedom which are stuck at every point, which have been pasted at every point, and this is what we call as the field phi of X. And now the natural question to ask is, what is the action of the symmetry G on this field phi, namely the configuration of the degree of freedom, which is this field? How does it act on phi? So, naturally, if it acts on phi, it will give me a new field which is phi prime. So, I have to find a way to describe what is this field phi prime. So, there is a very natural rule for doing this. So G of phi is phi prime of x. So what is this x? So this x is some point in the arena. To find what is the value of the new value of the field at the point x, find out where that point came from before you did the transformation, and that would be this point, which is G inverse of x. This is the point, G inverse of x is the point which was mapped to the point x by the action of G. And then you find the field at that point, and that is what we assign it as the value of the field at phi prime at x. Okay. I must point out that this is not the most general form, but this form will suffice for us in our discussions. Okay. So I will show you this by an example. So imagine that I have a big periodic box, continuum box. It's some kind of box, is like a cube of size L, as we have seen in previous lectures. And what we do is we think of a translation by a d-dimensional vector, right? And so this G here is TA, and it acts as the following. When TA acts on a field phi, it gives me a new field phi prime. And the rule to get this is that phi prime of x is phi of x minus a. Why is it phi of x minus a? X minus a is the point in the arena which would be mapped to this point x by the translation A. Okay. So I have a picture to show you this. So this was the original field which is phi of x. It's shown in red here. I did the translation, and when I did the translation, this point x went to x prime, which is x plus a. And how do I find phi prime of x? So just imagine that x is some point here, right? So imagine this point is here. You have to find out which is the point from which it came. So you hit T inverse a of x, so you will get x minus a, and that would be the so the value of the field at phi at the value of the field phi prime at x is the value of the original field at x minus a. So this is how we implement the symmetry action on the arena symmetry actions on fields. So now that you have seen this, I invite you to work out what is the action of the inversion operation. Inversion operation takes x to minus x. I invite you to figure out what is the action of the inversion operation on the field phi. Okay, we have seen what happens, how symmetry works in continuum arenas. Now let's see what happens in lattice arenas. Okay, first point is that if you are in the lattice arena, you have to be a little bit more careful with the symmetries, because the first thing you notice is that if you think of translations, you cannot translate by arbitrary amounts. So you can only translate by lattice vectors. So this is what I am showing here, that's a lattice vector. And so similarly, reflections and rotations, etc., cannot be arbitrary. So for example, if I take the square lattice and I think of rotation about this point that I am pointing out here, this red dot that is showing up on the screen, I cannot rotate by, for example, 60 degrees, because that will change the character of the lattice. I could try to do a pi by 2 rotation, right? Or I could do a pi by, I think that there's a mistake here, there's a pi by 2 rotation. These are the, so it's, you can only do a few set of transformations that are possible. So what this means is that lattice symmetries are discrete in the sense that they depend on, and they are discrete in the sense that you cannot do them continuously, they are sort of constrained by the structure of the lattice, and the symmetries themselves will depend on the type of lattice. So for example, the square lattice symmetries will be different from the triangular lattice symmetries, and so on. Okay, just as the continuum arena, lattice symmetry can also act on the lattice sites themselves. For example, under the action of translation, this site I can be thought of as being taken to that site, I plus L, right? So suppose I have configuration of some degrees of freedom, which I will call as phi I here, right? Then C, this configuration C is transformed by G to some new configuration, just like in the continuum case. So C goes to some C prime, which is formally given as action of G on C. Okay. So the natural rule again is you find out if what is the value of the field, what is the value of the degree of freedom at the site I, you figure out where the site I came from before the transformation. So that's given by G inverse, and you take the value of the degree of freedom at that site, and that is the natural rule. That it's quite analogous to what we did in the continuum. Okay. So take phi to be the Ising spin configuration and apply translations to see an example. So what happens here? The S prime, the transformed spin configuration, is obtained by, if I translate by a lattice vector L, is obtained by finding the lattice vector which, the lattice site I, which becomes the current site I. You find the lattice site which was the pre-image of before the transformation, and you find the spin configuration there and attach it to the site I, and that will be S prime I. Okay, so you can work out what happens in the Ising case for pi by 2 rotation. Okay, this should be pi by 2. I'll change that in the notes. Okay, now that we have seen the arena symmetries, both in the continuum and the lattice, we will move to internal symmetries. Internal symmetries act only on the degrees of freedom. They don't do anything to the arena. Okay, the Z2 symmetry is, of the Ising model is an example, right? And we have also seen a similar example of real scalar fields a couple of lectures back. Okay. So in general, the degree of freedom at each arena point could be a vector, tensor, etc. It could be any of these things. So let's consider a simple example. In the continuum, my degree of freedom, I say, is an n component vector phi alpha. These components I want to emphasize here are not components relative to the spatial coordinate axes. These components are components related to some internal frame of reference of the system, of the degree of freedom. For example, in the Ising case, some internal spin direction was chosen, this is what we call as the C axis, and that is sort of stuck to the to space, if you wish, right? So this is what I'm saying. So if the n component, if n equal to 1, this is our real scalar field. That is, it has only one component, it can take a real value, and this is what we call as a one component, and the coordinate can be the coordinate, this alpha equal to 1 can be thought of as the C axis. Similarly, an n component vector is denoted by phi alpha, alpha going from 1 to n, and there are some n independent axes in the internal space of the degrees of freedom. Okay. Now we can think of introducing a symmetry operation using this n component vector. So think of an n by n orthogonal matrix with elements R alpha beta. So R is the matrix and R alpha beta are the elements, R alpha gamma are the elements. This acts on the field phi. Phi here is denoted in bold, which is like a vector, as the following. It takes it to a new field configuration phi prime, which is the image of R, which is the image of phi by the action of R, and this phi prime alpha of x is obtained by taking the phi at the same point x, right, and operating on acting on it by this orthogonal matrix. So what it does is it rotates that vector in the internal space. Okay, and the phi fields are therefore representations of a continuous ON group. Okay. Now remember, if n equal to 1, this O1 would be Z2, and therefore it is actually a discrete group when n equal to 1. Very analogously, we can also realize ON internal symmetry in a lattice arena. And what you do is, at every lattice site you attach an ON vector, and the transformation rule is quite analogous. So you go to find what is the new field at a given lattice site, you find the old field at the given lattice site and just transform it by the orthogonal matrix. That is what we mean by global. Global meaning that this orthogonal matrix is acting in a very similar way, in exactly the same way at every site. So, like I pointed out, internal symmetries can be discrete or they can be continuous, like On when n is greater than or equal to 2. Okay. So now I will invite you to work out an interesting problem. Try to attach degrees of freedom on the sides of a square lattice, which transforms as a representation, as a non-trivial representation of S3. S3 is the permutation group of 3 objects. You can also think of it as the permutation group of a symmetry group of equilateral triangle. Okay. So we have seen that there are 2 types of symmetries, the arena symmetries and internal symmetries. We have seen how these can be implemented in different arenas, whether continuum arena or lattice arena. What we are now going to do is, we are going to put all of these things together and demand that the Hamiltonian is also invariant under the symmetry operations, and we will find what is this conditions imposed on the Hamiltonian by the symmetry, in the sense that we will be able to figure out what pieces of the Hamiltonians are allowed, and this will allow us to answer the question of the nature of the Hamiltonian, its uniqueness and whatnot. So this is what we are going to be after. Okay. So the collection of all symmetries, both arena and internal, you take them together and it will form a symmetry group G, right? This will be the symmetry group of our system. So the symmetry group of the Ising model on the square lattice will be all the square lattice symmetries and the Z2 internal symmetry taken together. So you could compose these symmetries and create new symmetries and so on. So the arena is a square lattice with periodic boundary conditions. The degree of freedom are the Ising spin configurations. So we have chosen this Ising spin configuration here. There is a typo here, that there should be a set of all SI. And the Hamiltonian is given by this expression, that is Z2 invariant, and this we have seen in a couple of lectures back. So what we said was that if you just impose internal symmetries alone, then the form of Hamiltonian with 2 spin interactions is the following. That is, you take every pair of sides in the lattice, you can take any pair of sides and say that there is some kind of exchange coupling J associated with that pair. This is just a real number, and it just finds out the interaction between these 2 spins. Now we impose arena symmetries. So for example, if I am going to first impose square lattice symmetries, I will first impose the translations. So when I impose translations, I invite you to work out the details. You will find that, take this particular side which I am pointing to on the left side here, and this side, they have a lattice vector separating them, indicated by this brown line. These 2 sides also have this lattice vector, which is the same lattice vector as the other 2 sides. So the claim is that if there is translational symmetry in the system, the exchange coupling connecting these 2 sides and these 2 sides have to be the same, because I can translate this side to that side, and then this J corresponding to this will move to that, and then you will find that they have to be equal. So the symmetry imposes a constraint that this J between pairs of sides depends only on the lattice vector connecting the sides. So this is a very, very strong constraint on the exchange coupling constants that we have. Okay, now we say, oh, we want to also impose rotational symmetries. So when I impose rotational symmetries, I will find that the coupling constant not just depends on the lattice vector connecting these 2 sides, it only depends on the magnitude of the lattice vector connecting these 2 sides. So for example, there is a J1 which is the exchange coupling between the nearest neighbors. So you see all these red links indicated here, they are nearest neighbor links. They connect sides that are nearest to each other. So all of these will have to be equal, and you can work this out yourself, it's not very difficult to show that these have to be equal if there is square lattice symmetry imposed. Okay, so we can now see that the number of coupling constants have come down drastically. So you will see that there is a coupling constant associated with the nearest neighbor interaction, which is what we call J1. There is another exchange coupling constant related to the second neighbor interaction, that is next near neighbor interaction shown by this Kion line here, and so on. So the Hamiltonian now has two parameters. J1, J2 I have written. You can of course go to the third neighbor interaction, put a J3 and so on. So you can write down all these things, right? And you see we have changed the notation from pairs of sites ij to these sort of angle brackets. One angle bracket indicates that they are nearest neighbors. Two angle brackets indicates that they are next nearest neighbors and so on. So now we see that the Hamiltonian has picked up certain energy scales. What are the energy scales in this problem? The intrinsic energy scales are J1 and J2 and so on. These are the intrinsic energy scales. So this is what I pointed out. The Ising Hamiltonian now possesses all these symmetries are all the symmetries, namely the translational symmetry, rotational symmetry, the Ising spin, internal symmetry. If you include all of this, then you will see that there are the coupling constants for two spin interactions are described by simply the nearest neighbor coupling constant, the next nearest neighbor coupling constants and so on. So formally there are infinite number of coupling constants because you know if I have taken infinite lattice, I can have interactions between spins at any neighbor length. Okay. So these are examples of the intrinsic energy scales of the system. Intrinsic meaning given by the system, and symmetry cannot tell you what the values are. These have to be obtained from experiment, or you have to postulate something and do a calculation and compare with experiments or whatnot. Okay. Now in any given problem there can also be extrinsic energy scales that you are providing. So for example, temperature is a very nice example of this extrinsic energy scale, right? So if I think of writing the partition function of this problem now, the partition function of this problem is depending only on the dimensionless ratios of these intrinsic scales with the temperature. So you see, because what happens is when I take e to the minus h by t, you will see that everything will be a function of j1 by t, j2 by t, etc. So the physics of the problem will depend only on such dimensionless ratios. Okay. So this is the most important and interesting observation from all of this consideration, that what enters the physics finally are certain dimensionless ratios of energy scales. They could be intrinsic energy scale, extrinsic energy scales, whatnot. And this suggests that we should study phase diagrams. After identifying the important energy scales in the system, we should figure out what are the important dimensionless coupling constants, and we should study the problem in terms of these dimensionless coupling constants. Okay. So now I am ready to tell you the Ising model, meaning the model that we will be using to study statistical mechanics throughout this course. So this is going to be a very simplified model, and the model is the following, right? The simplification we are going to make is we are only going to keep the nearest neighbor coupling. So I am simply going to take all the J2, J3, all of those guys are gone. All I have is J1 and I simply call it J. So the model on the square lattice, for example, is given in a very simple way now. For any given Ising spin configuration C, the energy is given by sum of energies associated with nearest neighbor bond determined by this energy scale J. If J is greater than 0, then energy is reduced by having nearest neighbor spins point in the opposite direction, and so this is called as the anti-ferromagnetic Ising model. And if J is less than 0, then you prefer spins on the nearest neighbor links to align parallelly, and this is what is called as the ferromagnetic Ising. If I don't mention during the discussions that follow, we will always be talking about the ferromagnetic Ising model, and this will be the workhorse of this course. and just anticipating certain calculations that are going to come up. Remember that J less than 0 was the ferromagnetic Ising model. We write for ferromagnetic Ising model, keeping the value of J positive, we write it as negative J, so that this whole thing, this whole quantity that I am pointing here is negative. And this is what we will call as the ferromagnetic Ising model, and the interactions are within only between the nearest neighbors. So what is the dimensionless coupling constant in this problem? So dimensionless coupling constant is J by T, that is this Ising exchange constant divided by temperature, and this is the quantity that will play a crucial role in finding out the phase diagram and so on. Okay? Alright, now I have an interesting challenge for you. So remember, here I talked about two spin interactions. I was saying that, okay, let's only think of pairwise interactions between spins. But if you think about it, you can have higher spin interactions. What do I mean by higher spin interactions? Say for example, I am asking you to consider the following thing. If you look at the square lattice can be made of a bunch of plaquettes. Plaquettes are elementary squares of the lattice. And if you look at a plaquette on the square lattice, you will see that it has 4 spins or 4 sites at its corners. So the left corner is what we call as site 1, and the bottom right corner is called site 2, the top right corner is site 3, and the left top corner is called site 4. So you could ask whether, can I write a term like this? Is it Ising symmetric? I invite you to work out whether this term is Ising symmetric, and you can have an energy scale associated with that interaction. So this is what I call J plaquette interaction. So is this Ising symmetric? And if you find the answer is no, then it's okay, that's fine. But if you find the answer is yes, then why are we not considering it? Because symmetry allows this to be there. So this is something that you should think about, and maybe it will take some time for you to figure out the true answer to this question, and it's an interesting challenge, so please do think about it. Okay, so I'm ready to summarize this lecture now. So the key points of this lecture is that symmetry plays an extremely crucial role in constructing models, and in many cases it is inferred from experiments, but I also pointed out that today people are imagining symmetries and finding new physics that is possible in those, if those symmetries were present, and physicists are trying to construct systems where those kind of symmetries are realized. There are arena symmetries and internal symmetries. Arena symmetries of the continuum arena are continuous, and arena symmetries of the lattice arena are discrete. Internal symmetries can be continuous or discrete. And the Hamiltonian is constructed typically by first imposing the internal symmetries and then imposing arena symmetries to figure out what are the key scales in the problem. The Hamiltonian itself will possess many intrinsic energy scales, and the competition between these energy scales can give rise to phases. And the phases can also be influenced by extrinsic energy scales such as temperature, etc. And the main thing that we discovered by the study is that the overall phase diagram should be thought of in terms of some dimensionless coupling constants. This is what will simplify the problem both from the computational perspective as well as from conceptual perspective. So what's coming up in the next lectures? So we have set up the framework for discussing phases and phase transitions. The next question to ask is, how do I find in a calculation that I am in a certain phase? How do I characterize a phase? So you'll also remember when we talked about solids in the first lecture, we said that solids are characterized by the resistance to shape change. So can I compute, can I go and calculate the responses of such phases to stimuli? And this is what we will take up in the next lecture. So thank you very much, and I hope your day has gotten a little better. Thank you.